Okay, so this last bit is on counting problems, which is really just anything involving permutations. And remember the formula for permutations on your formula sheet. NPR is n factorial over n minus r factorial, where n is the total number of objects, and r is how many of them you are arranging. This is where order matters. Often places where order matters if you're choosing people for specific positions or you're putting something in a specific place. NCR, often written like this with the n and the r, is n factorial over n minus r factorial, which you'll notice is the same as permutations. But because the order doesn't matter, we also divide by r factorial, which takes out the order. And again, n is the total number of objects, and we are using r of them. And we say n choose r. And in this case, the order does not matter. So think about something like choosing, getting a bunch of cards dealt to you. It really doesn't matter what order the cards come in. The yearbook committee is a group of 6 girls and 4 boys. They go to the foyer where there are 8 girls and 8 boys hanging out. How many different groups of 6 girls and 4 boys could they take a photo of if the order does not matter? Okay, so order does not matter is a combination. And often in that case, I like to do it like this. So there are 8 girls. We need 6 of them. There are 8 boys. We need 4 of them. So 8 choose 6 times 8 choose 4. Fire this up, see if it's working. Clear. 8 math over probability 3. 8 choose 6 times 8 math. Oh, wait. Delete. Okay, so make sure you kick up there. Times 8 math over to NCR 3, 8 choose 4. And we have 1,960. That could just be a group hanging around as a group. But if they decide to line the students up in a row with 6 girls first and then 4 boys, how many different arrangements of the group of 16 people are there? So you do this 2 ways. One would be the fundamental counting principle. 2, 3, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 6 girls and then the 4 boys. So 6 girls. So there are 8 girls, so we have 8 choices for the first. That's 7, 6, 5, 4, 3. 1, 2, 3, 4, 5, 6. And then for the 4 boys, we have 8 choices, then 7, then 6, then 5. So 8 times 7 times 6 times 5 times 4 times 3 times 8 times 7 times 6 times 5, which is 3 billion, 868,800. Okay, so that's fundamental counting principle, but also we could do 8p6. So there are 8 girls, we want all the arrangements of those 8 girls, and when you're in a row, you can tell them apart, times 8p4. So 8, number 2 is p, 8p6. Okay, now remember to move up, times 8 math, arrow over, number 2, 8p4. And of course, we're going to get the same number. So either way you want to do it, you could do fundamental counting principle, you could do it as a permutation, and just be aware that maybe they show the answer in this form, right? And you'll end up with something like 8 choose 6, 8 choose 4, with you deciding, is it a permutation and the order matters, or is it a combination where they don't? A dodgeball tournament allows 12 players to start each game. If the Warriors have 20 players, how many different groups of starting players could they have? So we're going to assume there's no real positions on this. We just have 20 players. So a group of starting players, right? Wouldn't really matter what position they were in. So this will be 20 choose 12. 20 math probability 3 choose 12 is 125,970. If the first group of starting players has to stand in a certain position in the end zone, how many arrangements of these 12 starting players? So if you're in a certain position, then that is a permutation, and we would be looking at 20p12. So 20 math over the probability number 2 for permutation 12, and we get a really big number. So 6.03 times 10 to the 13th. Okay, so 10 to the 9th is a billion, 10 to the 12th is a trillion, so that's like 60 trillion. Cards. Given a standard deck of 52 cards, how many different 5-card hands can be dealt that contain at least 4 black cards? So again, let's think about what is at least 4 black cards. So 4 black cards or 5 black cards. So 4 black cards, there are 26 black cards, 26 choose 4. We have 4 of them, then we have to have 1 red card, so 26 choose 1. So 4 black and, so we're multiplying, 1 red, or, so we're adding, 26 choose 5, that would be the black. If you like, and you probably wouldn't necessarily see this, but you can put 26 choose 0. And again, what I like is that the top numbers add to 52, the 52 cards, the bottom numbers add to 5, which are the 5 cards that we are choosing. And that will be 26 math and CR, right? Choose, we don't care about order. 26 choose 4 times 26 math in CR, 26 choose 1 plus 26 math in CR 5. And I'm not going to do the 26 choose 0 because we don't need that. 26 choose 0 or anything choose 0 is just 1. And we have 454,480, 454,480. How many different 5-card hands can be dealt that contain less than 3 hearts? So how many hearts can you have if you have less than 3 hearts? You could have no hearts, or 1 heart, or 2 hearts. Okay, you can't have 3 because you have to have less than 3. Now the only other possibilities are 3 hearts, or 4 hearts, or 5 hearts. And if I work that out, it's still, we would have to actually do more work than doing this. So no hearts, 13 choose 0. There are 39 other cards. Right? So deck of cards is split into 4 suits. Hearts is one of those suits. And okay, so I just wanted to come here just to show you a deck of cards. So there are 13 ranks: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. The jack, the queen, and the king are called face cards. So there are 1, 2, 3, 4, 5, 6 black face cards, 6 red face cards, a total of 12 face cards. There are 4 suits: clubs, spades are the black ones, hearts, diamonds are the red ones. So there are 13 hearts. That's here. There are 13 hearts. There are 13 of each. And 52 cards. So there are 39 cards which are not hearts. So 39 choose 5. Or 1 heart. 13 choose 1. 39, and we need 5 cards in total, so 4. Or, which is plus, 13, choose 2, 2 hearts, and 39, choose 3. And that is equal to 13, math, it's going to take a while, 3, 13, choose 0. Okay, make sure you kick up. You want to be up on the same line. 39, math, choose 5. Or, right, remember plus, 13, choose 1. Math, choose 1. And, right, this is multiply, and, so 1 heart and 4 non-hearts. 39, choose 4. Okay, and move up. Or 13, math, choose 2, and multiply 39. Those are the cards which are not hearts. Choose 3. And here we go. 357,862. So that is a lot. Because, let's just look, that is a lot. Because the total number of hands, 5-card hands, is 52. Math, choose 5. Total number is 2,598,000. So most of those, most of the ones contain less than 3 hearts. Most of the hands contain less than 3 hearts. How many different 5-card hands could be dealt that contain at least 1 diamond? All right, at least 1 diamond is 1 diamond, or 2, or 3, or 4, or 4 diamonds, or 5 diamonds. Now, the only thing else there is no diamonds. So what we can do is take our 52, choose 5, all possible hands. From that, let's subtract the ones that contain no diamonds. 13, choose 0, 39, choose 5. So this is all possible hands. These are the ones with no diamonds, and then what we'll be left with is the hands that contain 1 diamond, or 2, or 3, or 4, or 5, and instead of having to do something like this, we can simply do this. So I've already done the 52, choose 5, so I'm just going to go minus, so it'll pull that number in, and we'll go 13, math, choose 0, okay, and remember to kick up to get off that line, 39, math, choose 5. And we get 2,023,000, so 2,023,203. How many different 5-card hands could be dealt that contain a pair of 10s? Okay, so there are 4 10s in the deck, and we need 2 of them, right? So there are 4 10s. Let's clean this up. Here are the 10s. There are 4 10s. We need 2 of them. That can be done in 4 choose 2 ways. And then, back to the deck. So that's 4 out of the 52 cards. So there are 48 cards remaining, which are not 10s. So 48, choose 3. And so 4, math, choose 2. Okay, remember to kick up off the line, 48, math, choose 3. And that's 103,776 of the 52 choose 5, right? 2.5 million. How many different 5-card hands we don't contain 3 kings? So 4 choose 3. There are 4 kings. We want 3 of them. There are 48 cards. We need 2 of them. So 4 choose 3. So I'm going to reuse that. So 48 choose 2. 4 choose 3. And 48 choose 2 is 4,512. 4, 5, 1, 2. A basketball team of 11 players is to be chosen from 17 available players, which includes Jeff and Brett. In how many ways can this be done if both Jeff and Brett must be selected? So we don't care about the order. We're not picking them for a particular position. We're just choosing a team of 11. So let's say we have one Jeff and we want one of them. And one Brett and we want one of them. And there are 15 players left and we need 9 of them. Now, 1 choose 1 is just 1. So this whole thing will just be 15 choose 9. So 15 math choose 9. 5,005. Palindrome. Means the same forwards as backwards. Jeff and Brett cannot both be selected. Okay, so let's figure out what's going on here, right? The team could have both Jeff and Brett, neither Jeff nor Brett, right? So both of them aren't on. It could have Jeff but not Brett, or not have Jeff and does have Brett. Okay, so they both cannot be selected, which means we're dealing with one of these scenarios. Neither of them, this. Now we have this number, right? We have this. We know what this is. Both of them being selected is 5,005. Now if we just take 17, choose 11, that's the total number of ways we can pick the players. We don't care about anything. And from that, we will subtract the 5,005, right? Because those are the number of ways where they're both on the team. And then what we're left with is the other 3 possibilities. Neither of them are on the team. One of them is, but the other one isn't, or vice versa. So 17 choose 11 is 1, 2, 3, 7, 6. And from that, we can subtract the 5,005. And we get 7,371. Okay, so it's how we look at it, right? And remember, there are these 4 possibilities that you have to take into account. So when we say they cannot both be selected, it doesn't mean this, right? That's where they both aren't, but one of them could and the other one isn't, or vice versa. How many arrangements are there for the letters monotonous if there are no restrictions? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters is 10 factorial. But O's, we have 1, 2, 3, 4 O's. So we have to divide out the order of those 4 O's. Okay, anything else? We got an N. No, we got 2 N's. 2 factorial. That's the O's and N's. So anything else? M-T-U-S? No. And that is. So let's clear this. We'll go up top. So 10 math 4. Okay. Divided by. Now I need to divide by that product, so I'm going to have to put a bracket around that. 4 factorial times 2 math factorial. Okay, so you have to take the top. This fraction bar means work this out, then do the division, and that's what will happen here. And we get 75,600. each arrangement must begin with a T. So there's only one T, so let's mon, O, P, ton, O, US. Okay, it's got to begin with a T. Just take the T out. And then say I have 1, 2, 3, 4, 5, 6, 7, 8, 9. But 4 of them are O's, 2 of them are N's. So really, I can just bring this back down, go over here, delete the 1, put in a 9, hit enter, and we get 7,560. Okay, you have to lead with an T, with a T. Each arrangement must begin with an O. T, O, N, O, S. Okay, same thing. Take that out. So 9 letters left, but there are now only 3 O's. And we still have our 2 N's. And I can go in here. So all we need to do is change 4 to a 3. So we'll bring that back down. So lazy. And that's 30,240. 30,240. Each arrangement begins with exactly 1 O. Okay, so it begins with an O. Then our next letter is not an O. Not an O. And now we have that sort of same problem, right? If the next letter is an N, then there will be 3 O's that repeat, but not 2 N's repeating. And if the first letter is not an N, then we will have repetition on both sides. And so, okay, wait, let's slide this up a bit. Each arrangement begins with exactly 1 O. Okay, so we're going to cross off that O. Our next letter is not going to be an O. But we run into problems because if it's an N, N. Okay, so let's say that's an N. Let's cross off that N. So now let's look at what's left. So we have 1, 2, 3, 4, 5, 6, 7, 8 letters left, which can be arranged 8 factorial ways. 1, 2, 3 of them are O's, and now there's no other repeating letters because that was an N. But what if, well, we can work this out. So 8 factorial divided by 3 factorial. Let's clear that. 8 math. Factorial divided by 3 math. Factorial is 66,720. 6720. That's that guy. Now, what if it's not an N? Let's just put that back. M-O-N. Okay, so we're using an O. Okay, let's do not an N, any other letter. Doesn't much matter. So now, what do we have? 1, 2, 3, 4, 5, 6, 7, 8 letters again. But 1, 2, 3 of them are O's, and 2 of them are N's. And that's going to be, well, basically, it's just that number there divided by 2. Right, 2 factorial is 3360. 3360. So 0, 8, 0, 10. 10,080 of the ones that begin, of these, begins with an O. See, this and begins with an O. It could be 1 O, or 2, or 3, or 4 O's. It's 30,420. The ones of those that begin with exactly 1 O is 10,080. If they begin with exactly 2 O's, all right, let's write it out again. 1 O, begins with 2 O's, take these guys out. And we basically have to run through the same reasoning as there, right? Because if the next letter is an N, then we won't have repeating N's. So let's do that. Let's just say the next letter is an N, this guy. So we'll have 1, 2, 3, 4, 5, 6, 7. Okay, that was 1. So there's 7 letters left. The next one is an N. So we have, right, so we took out the 2 O's. Next one's an N. That's gone. So 1, 2, 3, 4, 5, 6, 7. But we have 2 O's. And no other repeating letters because of that N. And that is 7 math factorial divided by 2 math factorial is 2520. And then, okay, so we've got the same idea. Let's go back to what we have here. M-O-N-O. So it begins with 2 O's. Then we did the one where the next letter was an N, but what if the next letter is not an N? Okay, so we have 1, 2, 3, 4, 5, 6, 7 again. So 7 factorial. But we've got 2 O's and 2 N's. Right? That's going to be half of that, which should be 1, 2, 6, 0. And add those two together, right? It's going to be an OR. So 0, 8, 7, 3. 3,780. 3,780 will begin with, so that's of these, right? Of the 30,240, 3,780 of them will begin with exactly 2 O's. Each arrangement ends mon o. All right, so take all the O's out, right? Because it ends in 4 O's. And then we just have 1, 2, 3, 4, 5, 6 letters to arrange. 2 of them are N's, and that is 360 ways in which each arrangement ends in all 4 O's. And the last little bit. There are 5 web-based journalists and 7 print-based journalists available to cover a trial. How many possible groups of 4, so we want to have 4 in total, 4, can be formed if the groups must consist exactly 3 web-based. So 5 choose 3, there are 7 print-based, and we need 1. So there are 12 in total, we need 4. So 5 choose 3 times 7 choose 1. Now anything choose 1 is just the number, right? So we'll go 5 choose 3, which is 10. So this will be 10 times 7, which is 17. Group must consist at least 3 web-based. So that's 3 web-based or 4 web-based. Okay, and the reason we only want 4 journalists, so 3 or 4. So 5 choose 3, 7 choose 1, or 5 choose 4, 7 choose 0. All right, so we know what that is. That first bit is 70. Well, let's do it. So it's 10 times 7 plus. So 5 choose 4 is 5 times 1, and that will be 75. The group must consist of at least 1 print-based journalist. So that's 1 print-based, or 2, well, use the word or 2 print-based, or 3 print-based, or 4 print-based. Now, if we think about it, what can we have in the way of print-based, right? We can have none, or 1, or 2, or 3, or 4. So there's also no print-based, right? And if we did that, that would be all the possibilities. So what we want is, what we're going to do is take all arrangements minus no print-based. And what's that going to leave? Well, if that's gone, then it's going to leave 1 or 2 or 3 or 4 print-based. So all arrangements is 12 choose 4, no print-based, so there are 5, right? So we could go 5 choose 0, no print-based, 7 choose 4, Oh, wait, print base is 7. So, where is it? No print base. So 7 choose 0, no print base. 5 choose 4, which would be all web-based. So at least one print base is 1 or 2 or 3 or 4. What it isn't is there are no print base. So 12 choose 4, which is, let's work these out individually. 12 math over choose 4. 12 choose 4 is 495. And 5 choose 4. All right, let's do that the easy way. We'll bring that back down. We'll go over here, delete that, change that. So we have 5 choose 4 is 5. 495 minus 5 is 490 minus 9. 490 will have at least one print base. So 1 or 2 or 3 or 4 without us having to do 4 calculations, right? 7 choose 1, 5 choose 0, 7 choose 2, 5 choose, etc. So we can avoid doing all of that. And speaking of all of that, that is all.